Okay. So the first thing that you can see on your blue sheet is we have the reciprocal identities, and you don't really have to remember that that's what they're called, but you could remember that's what they're called. So sine is the same thing as 1 over cosecant. So when we were dealing with like the unit circle, we just remembered that sine is opposite over hypotenuse. And then cosecant was the flipped version of that. It was hypotenuse over opposite. And this is the same thing. It just looks a little different. So it's just saying, and you can write this or not write this. It doesn't matter to me. So if we're going to look at how the reciprocal identities work, reciprocal identities. We have that sine theta is opposite over hypotenuse. We know that cosecant theta is hypotenuse over opposite. I just want to show you guys that if you say that sine is the same thing as 1 over cosecant, I just want to show you that that really does make sense. So if I take the cosecant out and I replace it with 1 over hypotenuse over opposite, because that's what cosecant is, it's the hypotenuse side over the opposite side. When we do a whole number divided by a fraction, you can think of it as keep it, change it, flip it. Do you guys remember doing that? Keep it, change it, flip it. Or you can think of it as when I divide by a fraction, I always multiply by the reciprocal of that fraction. So keep it, change it, flip it if that's what's comfortable to you. Or you can say when I divide by a fraction, I multiply by the reciprocal of the fraction. Either one of those is fine. So I'm going to say keep it, change it to a multiplication problem, flip the fraction. Or when I divide, I keep the top and then multiply by the reciprocal of the fraction. And so this gives me 1 times opposite over hypotenuse, which is just opposite over hypotenuse. So you can see how sine is the same as 1 over cosecant. Everyone see how that works? Okay. And you can do that, you can prove that that works for all of these reciprocal identities. You can use the sides of the triangle. So we've got sine, cosine, remember, was adjacent over hypotenuse. That's the same thing as 1 over secant. We should not be having a continuous conversation while I'm talking up here. Tangent is opposite over adjacent. We know that cotangent is adjacent over opposite. So all of these kind of work that way. Now for the other one, we know that tangent was sine over cosine. We always thought of this as y divided by x. Do you guys remember doing that last unit? Y divided by x. Cotangent was x divided by y. So another way of saying that would be saying cosine divided by sine. Does that make sense? Okay, so we're not going to have to memorize these. We've got them on the paper. We just want to make sure we're familiar with them and that we can find them on the paper. Do those all make sense? Okay. Do you guys remember looking at sine squared plus cos squared equals 1? We just did it one time. We should go through it again. I'm looking at your faces and they look confused. Okay, so we're going to go through where that one came from again. Okay, so when we were filling out the unit circle, go ahead and draw a circle on your page. Oh gosh, that circle was good until it wasn't good. There's circular-ish. If you guys remember those notes that we were taking, we had this was like the first quadrant. And I kept having you guys, it had a line drawn like this, and I would have you guys take this point and I would have you guys drop it straight down. And I said this was the radius. It was a radius of 1. and I said this was the theta over here, and I said this was a point, it had an x-coordinate, it had a y-coordinate, and that for this triangle, this side right here was how we measured the x-coordinate, right? Because to get to the point, you go over the amount of x, and then you go up the amount of y. You guys remember doing that? Yeah. Okay, and so then we figured out that sine theta was opposite. This is the opposite side. Sine theta was opposite over hypotenuse. Remember that? Sine was opposite over hypotenuse, and since opposite over hypotenuse was y over 1, that's why we got sine theta equals y. Does that sound familiar? Yeah. And we said that cos theta was adjacent over hypotenuse, and so cos theta was x over 1. And that's why we said that cos was the x-coordinate. Does that sound familiar? Okay. So we said this was the x-coordinate, this was the y-coordinate. Okay. So if we took this, and we know that the radius is always 1 because this is a unit circle, and so unit circles always have a radius of 1. That's what unit means. It means 1. If we were to do the Pythagorean theorem on this triangle, this is a right triangle. If we were to do the Pythagorean theorem on that triangle, like a squared plus b squared equals c squared, but to do it with these given sides, what would we say for the Pythagorean theorem? Using x, y, and r. Okay, so the Pythagorean theorem would say x squared plus y squared equals r squared. Okay. And then if we look at the radius for this, because it is a unit circle, the r squared would equal what? 1. It would equal 1. Okay. So it would be x squared plus y squared equals 1. Okay. Does that make sense so far? Okay. And then if we say, well, cos is just the x value, then is it okay if I take the x out and put cos in instead? Okay. So I would say cos theta squared, and then I would take the y out and put sine in and squared, and sine in instead. So I would say plus sine theta squared equals 1. Does that make sense? Okay. Now, most people don't like to put all those parentheses because it's kind of cumbersome to write. It's not easy to write quickly. And so most people don't write cos theta in parentheses squared. Most people shorthand that and they write cos squared plus sine squared. It's just notation that means all of cos squared, all of sine squared, but it makes it so you don't have to write the parentheses. Okay, does that make sense where that came from? Okay, so this they call the Pythagorean identity. And that's on your blue sheet. So sine squared plus cos squared equals 1, or cos squared plus sine squared equals 1. And that identity is really handy. We're going to run into that this unit. Okay, so we know where that came from. Now, if we look at the blue sheet, how do you think they got these other two?
Wouldn't that be like finding the a or b value?
Yeah, kind of. Yeah, if you have a squared plus b squared equals c squared, it's kind of like they isolated the a squared, and then they subtracted the b squared over to the other side. So they said, okay, let's keep the cos squared where it is, and let's minus the sine squared over to the other side. So they said, okay, keep the cos squared where it is, and then have 1 minus the sine squared over to the other side. So then they said, okay, this is just, if you have the Pythagorean identity already, here's just another piece of information we can get from it. Does that make sense? Logical information you can get from it. And then they said, okay, well, we can do the same thing with sine. If we have sine squared and we want to isolate the sine squared, we could just leave the one right here and take the cos squared and minus it over. So if I want sine squared to be isolated, that would just be 1 minus cos squared. So we have the original Pythagorean identity, and then we have how you would get cos squared isolated and how you would get sine squared isolated. And so that's where the other two came from. Okay. Does that make sense? Okay. Now, the other two are kind of interesting. I'm going to show you where those came from. So these ones we're going to start with cos squared plus sine squared equals 1. And we're going to say divide by cos squared, divide by cos squared, divide by cos squared. And then we're going to go through and we're going to simplify this. So what is cos squared over cos squared? That's just 1. Same thing over itself is just 1. Okay. Now, sine over cos is something specific. Anyone know what sine over cos is? Tangent. So if sine over cos is tangent, then if we have sine times sine over cos times cos, what would that be? That'd be tangent squared. So sine squared over cos squared is tangent squared. Okay? Okay? And then over here, we have 1 over cos squared, which is like 1 over cos times 1 over cos. And so what is that? Secant. Okay, so look at the other Pythagorean identities, and what do you notice? We just found one of the other ones. See where it came from? Okay. Now, we're going to handwrite in one more because sometimes the secant squared isn't the thing that's isolated. Sometimes it's the tan squared that's isolated. So if tan squared was the thing that was isolated, then what would you have? Tan squared equals what? Not 1 minus secant squared, but you're close. Secant squared minus 1, because you'd be taking the 1 and minusing it over to this side. So tan squared equals secant squared minus 1. Okay? Anybody have a guess about where they got the other one from? Yeah, take the original Pythagorean identity and divide by sine squared instead of dividing by cos squared. Okay, so we're going to go back to the original. So we're going to say cos squared theta plus sine squared theta equals 1. And we're going to divide by sine squared. And we're going to divide by sine squared. And we're going to divide by sine squared. Okay. So sine over cos is tangent. What is cos over sine? Cotangent. So if we have a cos times cos over a sine times sine, what is that? Cotangent squared. Okay? Sine squared over sine squared, 1. 1 over sine times 1 over sine. Cosecant squared. Okay? And then that's where the other one came from. We got the backwards version of it here, but with addition, you can switch the order and it's okay. So 1 plus cotangent squared is cosecant squared. All right? What if we wanted the version where cotangent squared was all by itself? Okay, cotangent squared is cosecant squared minus 1. Okay. All right, how do your brains feel so far? Do you guys see how what we've just done is all we did was like substitute things in and out and see how they equaled something else, okay? And one thing that we were careful to do as we substituted things in is we were careful to make sure that the things that we'd learned about math were still true. So if you had something divided by itself, that thing should equal 1. If you had something squared over something squared, we made sure that, that doesn't become just like that squareds held true. If something was a squared, then it stayed a squared. Does that make sense? We had cos squared over sine squared was cotangent squared. We didn't say cos squared over sine squared was cotangent. We kept holding on to the things that we had learned about mathematics and made sure that they made sense. So that's one thing that we're going to be careful of when we do this unit. So this unit is a lot of substitution, but also being careful that the stuff that we've learned about math, we're still remembering that stuff those rules about math still have to apply. Okay? All right, so now we're going to get into an actual problem. So here is an example we're going to go through, and we're going to take our time, and if you get stuck, you're going to ask for help sooner rather than later. Do not silently struggle with this unit, okay? So the first problem that we're going to do is we are going to simplify 1 plus sine x times secant x minus tan x. We're going to simplify 1 plus sine x times secant x minus tan x. Okay? And when we simplify, there's a method that we're going to use to do this problem, and this method doesn't work for every problem, but it is a method that often works. So it doesn't work every time, but it is a good method to try. And the method is to convert everything into sine and cosine. That's the method. Okay, now the reason that method is good is because the original problem is written as just regular identities. The original problem is not written as squareds. If I saw squareds in the original problem, then I'd be looking over here for my substitutions. But the original problem doesn't have any squareds. It only has these types of identities. And if I look over at these types of identities, sine, cosine, cosecant, secant, all of these can already be written as sine and cosine. And then if it's tan or cotangent, those can be written as sine or cosine. So it's really easy to take a problem when it's written with no squareds in it and take all those pieces and rewrite them as sine and cosine. Okay? So I'm going to take the first piece and I'm going to leave it 1 plus sine x. That's already written as sine. And then for the second part, I'm going to rewrite those pieces. So secant x, how should I rewrite that in terms of sine or cosine? What is secant? It's 1 over cos. Okay, so that is 1 over cos. And then tangent, how could I rewrite that as sine or cosine? That's sine over cos. Okay? Now, what do you notice about this problem now that I've rewritten those two pieces in terms of sine and cos? They don't cancel, but what do you notice about them? They have a common denominator. And if you have two fractions with a common denominator, what can you do with them? Do they have to stay two separate fractions? No, they can become one fraction. Does that make sense? Okay, so now I'm going to rewrite this problem, and I'm going to take the two fractions in the second set of parentheses, and I'm going to write them as one fraction with a common denominator. Now from here, I basically just follow the problem doing math that I would normally do. So if this problem wasn't trig, if this problem was just like numbers and x's and y's, what I would normally do is I would probably make this a whole number. I would put it over 1. And then when I multiply two fractions together, I multiply the tops together, I multiply the bottoms together. So if I multiply the bottoms together, what is 1 times cos? I just get cos, okay? And if I multiply the tops together, I'm going to have to FOIL. Make sense? I'm going to have to FOIL. So I've got 1 multiplied by 1. I've got 1 multiplied by negative sign. Okay. Yeah. Yeah, with the eyes. Do you guys remember? It starts with a C. Do you guys remember what that word is? C-O-N-J. Conjugate. These are conjugates, yeah. Sine x times 1. So plus sine. And then positive sine times negative sine squared. Okay, so what happens with the two middle terms? They cancel out. Okay, so now we have 1 minus sine squared on the top, and we have cos x on the bottom. Now, at this point, you might feel a little bit stuck because cos and sine are different. They don't cancel out. And you couldn't cancel them anyway because this would kind of be like having like 1 minus x squared over y, if that makes sense. You've got like two different things on the top and the bottom. Those wouldn't cancel. But if you look at your blue sheet, you have something squared, which means you're going to be looking in the Pythagorean identities. And then you have a regular cos, which means you're looking over here. So I'm going to ignore the cos. The cos by itself can only become 1 over secant, and that's not particularly helpful right now. But if I look at the 1 minus sine squared, what can 1 minus sine squared become? It can become cos squared. So the top of this is cos squared. The bottom of this is cos. So the top is cos squared, the bottom is cos. The top is cos squared, the bottom is cos. So what do you guys think I can do? I can cancel 1 cos on the bottom with 1 cos on the top. So cancel 1 cos on the bottom with 1 cos on the top. My final answer is cos. Now the instructions told me to simplify. Does it seem like I've done that? Yeah. The answer is cos. Okay, so let's think about what we did. The method that we used was convert everything into sine and cosine, so we did that first. That was the one thing that we learned how to do that was different. Now, after that, I just did math that I would normally do in a simplifying problem. It looked weird because it was trig, but I did math that I would normally do. If I had something times a fraction, it would be normal for me to multiply those things out, right? It would be normal for me to FOIL these things. It would be normal if I had something times a fraction to make sure that I could multiply the bottom of the fractions. That's normal. Once I FOILed things, it'd be normal for me to cancel those. This part wasn't normal. Using my blue sheet to see what substitution I could make, I had to think about that. But then after that, this part here, seeing what could cancel, that was a normal mathematical step. So we used the method that we learned, and then after that, we kind of trade back and forth between doing normal math for us. What is math that I should do? I should have two common denominators. I should add those together. I have two parentheses next to each other. I should FOIL those. I have the same term on the top and the bottom. I should reduce those. Those are all normal math steps. Or I don't really know what to do. I should use my blue sheet. See how we went back and forth? Okay, so those are kind of the strategies that we're going to do as we work on these problems. Is I either do a regular math step that I've learned as a math student, or I'm going to use my blue sheet to make a substitution. Does that make sense? Yes? Kind of? Okay. And then the only way that these start to get more obvious is you do more of them. It's not going to be obvious from the beginning, but the more of them you do, the easier it gets. Okay? And I'm going to start you off on problems that are a little bit easier so it won't be as frustrating. Okay, let's try one more, and then I'll hand out a worksheet and we can get started. So this one says to simplify sine over cos plus cos over 1 plus sine. Now, one thing you have to do when you're doing these problems, I should never see somebody write this problem and say sine over cos plus cos over 1 plus sine, because there is no such thing as sine over cos like that. Remember, if you hit those buttons in your calculator, what does your calculator do? It puts parentheses. It automatically wants to know, sure, you want to do sine, but you want to do sine of what? So there is no such thing as sine by itself. It's always sine of an angle. Does that make sense? That is one thing I will consistently mark you down on. If I see, I'll mark you down on homework assignments, I'll mark you down on a quiz, I'll mark you down on a test. So if I see a trig function written without a theta next to it, or an x next to it, or a u next to it, or whatever, if you don't do that, I will consistently mark you down, because there's no such thing. That would be like you writing 5 plus 3, but you just wrote 5 plus. 5 plus what? Tell me what you're adding to it, because that doesn't make sense. Okay? So make sure you always have the theta next, because it has to have that for it to be mathematically plausible. Okay, so the method we're going to use here is really common for these problems, and we're going to be getting a common denominator. So when you guys were adding fractions back in the day, if you were to add like 1/5 and 1/3, and your two denominators had nothing in common, 1/5 and 1/3, what would you say the common denominator was? 15. And how did you get that? You just multiplied them together, right? 1/5 and 1/3. Same thing we're going to do for this one. Cos theta and 1 plus sine theta, they don't really have anything in common. So I'm going to say my common denominator is just both of them. This is kind of like the 1/5. This is kind of like the 1/3. My common denominator is going to be both of them multiplied together. So I'm going to start with the sine theta over cos theta. And I'm just going to multiply it by the denominator of the other one. So I'm going to multiply it on the top and the bottom. 1 plus sine theta on the top, 1 plus sine theta on the bottom. And then I'll go ahead and I'll write the second fraction. and I'm going to multiply it by this denominator, and I'm going to multiply it on the top, and I'm going to multiply it on the bottom. So my common denominator is 1 plus sine theta times cos theta. You can see I have that for both of my fractions. So I've got 1 plus sine theta times cos theta. Okay, I want you to take a moment and I want you to write down what we have from this and what we have from this on the top of your fraction. So take a moment, write down what we have from this and what we have from this on the top of your fraction. What'd you guys get for this part? Sine plus sine squared. Did everyone get that from distributing the sign inside the parentheses? So sine times 1, sine times sine. We got that?
So it doesn't really matter, like, if it's in front of it, because normally it's a division.
You can distribute behind. Yeah, if we had 1 plus x times x, this is kind of what we have, same sort of idea. And then if we distribute from behind, it would be x plus x squared. This is the exact problem we did. We just did it with signs. Good question. Okay, and then for the last part, what do we have? Cos squared, okay? Cos squared, okay? So for our next step, we're still going to have that common denominator. But at this point, we don't have an obvious math step we could do. An obvious math step would be like, oh, I can combine like terms, or there's something I could cancel, or there's something that could be done like from my math history of like having taken math classes as a student. So since there's not an obvious math step to do, that means that I should be using my blue sheet. So I'm going to give you a hint. It's something in the Pythagorean identity. Something in the Pythagorean identity is going to help you with the next step. Sine squared plus cos squared equals 1. So right here, sine squared plus cos squared, all of this gets to go away because sine squared plus cos squared is just 1. So we have sine theta plus 1. Does that make sense? Okay. All right, at this point, we don't need the blue sheet. We can do regular math. What regular math do you see? Yeah, what cancels? 1 plus sine on the top, 1 plus sine on the bottom. Those cancel. And what is our answer at this point? Not cos. 1 over cos. Good. And according to the blue sheet, what is 1 over cos? Secant. Okay, is this simplified? Yes. Okay. How are your brains feeling? Good? Okay. We're going to start our practice worksheet, but we're going to work kind of slowly. If this is something that meshes with your brain and your brain feels good about it, feel free to work ahead on the worksheet. If your brain does not feel good about it and you want to go slow, then we can go slow and do some of these together. Okay? All right, I'm going to go ahead and hand these out. So the first few on the worksheet, they're specifically using the strategy of turning it into sine and cos. And then after the first 6 problems, I think, then it says to use whatever method. All right. So for number one, turn it into sine and cos. Turn all of it into sine and cos. For number one, turn all of it into sine and cos. For number one, turn it into sine and cos. And this problem should take you about 2 seconds. Did you turn it into sine and cos? Once you've done number one, do number two. Turn it into sine and cos. Number one and number two are very similar problems. Did we get number one and number two? Somebody tell me what to write for number one. Cosine times sine over cos. And then what happens? This cosine is over 1, right? Okay, and then what happens? The coses cancel. We've got a cos on the top and a cos on the bottom, and those cancel. And our answer is sine. Okay. Say it again.
Are we trying to get sin and cos?
You're trying to put it into sine and cos. So we don't know what the final answer is, but you're trying to convert it into sine and cos. What'd you guys get for number 2? So we have sine times cos times 1 over sine. And then the sine and the 1 over sine cancel. And we get cos. How are you guys doing with number 3? How should we rewrite secant squared? We're not using the Pythagorean identities. It's tempting, but we can't use them because the instructions said to use sine and cos. So secant is the same as what? Secant is the same as 1 over cos. So secant squared, 1 over cos squared. Tan is sine over cos. So tan squared is sine squared over cos squared. Okay, and then what do we do? We've got two fractions. They've got a common denominator.
And 1 minus sine.
Okay. Is this a math step we should be doing, or should we be looking at our blue sheet? This is a blue sheet at this point. So 1 minus sine squared is cos squared. So we have cos squared over cos squared. So our answer is 1. Okay, 4 is starting to get a little funky here. All right, so what's the top? Sine over cos plus, what's cotangent? Cos over sine. And then what's this part? Secant is 1 over cos times cosecant is 1 over sine. Yeah, we got to have a common denominator because we got two fractions. We can't put them together yet. So how do we fix it so they have a common denominator? So this one we have to multiply by sine over sine. And this one we have to multiply by... Okay, so this one's going to be sine over sine. And this one's going to be cos over cos. Okay, so the top of our fraction has sine x cos x for a denominator. And then what do we have up here? Okay, so sine squared plus cos squared. So there's the top. What should I write for the bottom? How do you multiply two fractions together?
Is it cos multiplied by 1 and 1 multiplied by sine?
Do you cross multiply if you multiply fractions together? You multiply straight across. So we get 1 times 1 is 1 cos times sine. Okay, and then what do we do if we have a fraction over a fraction? Keep, change, flip. Okay, so I'm going to keep the top. Sine squared plus cos squared over sine cos. Keep it, change it to a multiplication problem. Flip the bottom. Is there any math we could do? Like any? So cancel out, what are we, so we're canceling something. What are we canceling? Sine, cos, sine, cos. Sine, cos, sine, cos. Are we all in agreement over that? Sine, cos, cancel. Sine, cos. Okay. So we're left with sine squared plus cos squared. Is that the final answer? Oh, this equals 1. Do we agree that equals 1? Yes? It's the Pythagorean identity. Hey! Yeah, this is a fun Pythagorean identity that shows up all over the place. And you'll just be hoping to find it, because it just makes stuff disappear. Okay. I'm going to let you guys work. We're not going to rush it. We're just going to go slow. Huh? A U is just another angle. It's just like a theta or an x. They just mix up the variables for you. All right, let me know if you get stuck.